No, I did this one.
All right, we're going to start with 12 because that was by far the most requested. And you got the hot air balloon going up and drops the camera. So immediately, right away, camera is in free fall. That is kind of the key here. Camera is in free fall. So accelerating which way?
Accelerate downward.
Excellent. Yeah, that's about all you need to really write. I like to draw myself a little picture here because here's where the camera gets dropped, and that's some distance, right, above the ground. Do you not? What does the camera do? What does the path of it look like?
I don't know.
Which way is it moving?
It's down. So,
Moving up.
the camera's going up.
Well, the camera was traveling with the person in the hot air balloon. What's the hot air balloon doing?
Going up.
Ascending, which means up.
Well, so problem one, the camera.
And in problem two.
Oh, wait.
So the camera is going to go up until it does what?
Change direction.
Stops and changes direction.
Wait. So it has it up on like a let's go, and then it goes up.
Here, take your bottle of water. Move your hand upwards with it and just, no, turn it like this. Go like this. Does it keep going up? Try a little faster so you can see it better.
I don't know, I just think it will go so slow that you just like, so hot, let it be free.
Let's try it at a higher rate. Did it go up?
It's like really slow, then it just goes.
It's decelerating.
But it still goes up. It's just you can't. So increase your speed and see if it still keeps going up. I mean, really, what we're saying is the hot air balloon throws the camera upwards. That's the way to think about it, right? Because how do you throw something up in the air? You give it a velocity upwards, and then you stop touching it. That's exactly what the balloon, the person, is doing to the camera. Now, from the person's frame of reference, they will see it go up a little bit and then go down, but not quite as much as if you were on the ground. Because what is their initial speed, do they see? 0, right? Because it's moving up with them. So from their perception, they kind of see it just fall off. But from the outside perspective, it goes up before it comes down. And that's usually what messes people up. Because, remember, it's in free fall. Which direction is it accelerating? Down. The whole trip, it's accelerating down.
Wait.
It starts by moving up.
So, yeah, free fall doesn't imply that it's going any direction, right?
Right. Free fall is just another way to say, I'm accelerating down at little g. Just a short way of saying that. So that's my little drawing. Let's see what I need to calculate. I did do part A and B before. There is 27 meters above the ground. How much time does it take the camera to... Oh no, this one I did. This one only has A and B, right?
Yeah, I only have to.
There was another one that I was thinking of that I just did C and D. And what velocity does it have when it lands? Okay. So, equation-wise, what's nice is in reality, I don't care about the shape of this path at all.
No, it does.
Because all I care about is, hey, I know what it's doing at the start. Let me see what it's doing at the end. Who cares what it does in the middle? That's the beauty of displacement. Beginning to end, ignore the middle. So I'm going to use my equation that deals with displacement, which is this one right here in the middle. the big old one, also called your general kinematics equation, which I'm going to write down. Make sure my pen is still full. Okay. So I'm going to use that where I end up D is where I started, D naught, plus how I was moving when I started. I left off the delta. Yeah. These should be vectors too. Plus 1/2 how my motion was changing, t squared.
Is T naught where it
Started, yep.
That's where it started?
Yep.
Just put an I.
All not I, same thing. And actually, I use them interchangeably, so that when you get to college, and you've got someone who only uses one, you'll know what both mean.
So what's the first and second T?
Time and time. So if you use the same variable in the same equation, it has to mean the same thing.
What's the A is just the acceleration that it's initially going?
Sure. And the acceleration is going at any point. Because what's the acceleration always of this object?
7.9. That's what it says. It's going 9.81. That would be the answer.
Which direction?
Down.
There you go, good boy.
So also the negative acceleration but a positive initial velocity.
Well, do we want to call up positive?
Yes.
Okay. So I'm going to do a couple things. I'm going to call up positive, and I'm going to call this height 0 meters, the ground. Is that okay?
Yeah.
Okay. Because I could remember I got the power. I can do it anywhere I'd like. So let's see. Where I end up is at 0 meters. Where I started, I think I started at 27 meters. Yeah, I started at 27 meters. How was I moving when I started?
7.9.
7.9 up or down?
Oh.
So positive 7.9 meters per second, t, plus 1/2. Oh, I'm accelerating down the whole time, so negative, and I'm in free fall, so negative 9.81 meters per second squared, t squared. Cool, I have everything but t.
So now I just get everything on one side.
Now you just solve for t.
Yes.
If you have a TI calculator, that's easy. You can also, if you don't own a TI, if you go back out to that wonderful page of Physics is Fun, and you go down, you can use, I would suggest Wolfram Alpha as your solver.
So solve for T.
Solve for T. Yep.
Or you can do that by hand, old fashioned.
You could do it out by hand, old-fashioned way.
Why is it half? So
The reason that it's half, well, that's how the relationship is. But it has to do with how acceleration, remember the area under the velocity graph is the displacement. So each of these terms is actually a displacement term. So if the velocity times the time, that area is the displacement. The area of that area is the displacement also. That's why, and the 1/2 comes in because of the way the mathematics works, the way the relationship is. The easiest way to understand it is to use calculus, because calculus was invented to make physics problems easier to solve mathematically. I mean, that's the only reason calculus came about. It's been used for other things since, but that's its root purpose. So if I do what's called taking the derivative, I need this 1/2 for the mathematics to work out. All right, that's so. Oh, you don't want me to finish this one?
Yeah. Oh, no, oh.
Well, you just told me like that. Oh, today. You like live like speed. It's good live like speed.
So I already got an answer for mine at least of 3. Ooh. I forget this doesn't hold the thickness here when I just switch markers. 3.28584 seconds. And then I want to go on to do the second part, right? How fast is it going at the bottom? Well, I actually know so much information, I could use either of these equations. I think I'm going to use this one because it doesn't rely on the time. So if I screwed up the first one, and found the wrong time, at least I won't screw up the second part. All right? Oops. So I'm going to use the V final squared equals V initial squared plus 2A delta D. So the final velocity is the initial velocity plus 2 times the acceleration times the displacement. Right? So my final velocity, that's what I'm looking for. Most common mistake will be to forget the square. My initial velocity was what, 7.9 positive, I square that. Plus 2, my acceleration is negative 9.81 meters per second squared. And then my delta D, let's see, delta is final minus initial. Where do I end up? 0. Where did I start? So 0 minus 27.
You don't care that it goes up. It doesn't matter from the displacement, right?
Well, it goes from up to down.
Yeah.
That's why I end up with a negative displacement. Don't forget, you'll first have the final squared equals something, and then you get the answer in meters per second.
How did you get the cheese on the other side? You just divide it by t.
I just use the solver because I'm not a math teacher. I don't care how you solve it as long as you solve it. I don't care how you figure out how to spell words either, because I'm not an English teacher. Shannon, you make me smile. I may. All right, so we're going on to number 7 here. I was told part A wasn't needed to be done since you had a 50-50 shot on it, and I think you get more than one try. Okay, so if you can't get number 1, part A, let me know. We'll talk about the process. All right, so B, the stopping distance, you got this car, create a constant decel. Now, what do they mean by deceleration?
Acceleration.
Not necessarily. If I was moving in a negative direction and I applied my brakes,
Acceleration in opposite direction of motion.
that's the way to put it. Guys, that's another little thing you need to put into your brain somewhere. The definition of deceleration is acceleration in a direction opposite of motion.
Yes.
All right? Not negative, but opposite motion. So decel means a op
Lance decel.
motion. All right? So, probably about all you need in the Y there. You got this car moving at this. What does it mean to stop? What comes to 0? Velocity comes to 0. I'll switch to blue because it's better color. So I'm going to use the same one I used the last problem. So I'm going to end up at 0. In this case, I'm starting at 16. Oh, I picked positive for my 16. What does that mean I should pick for the sign on my acceleration?
Why are you using that equation?
Because I wanted to.
It's the one that works.
Well, that's actually a good question. Because I knew what speed I wanted, what velocity I was going to end up at, or what speed. I knew what speed I started at. I knew my acceleration, and they asked me how far did I go. So if I look at my equations here, this is the definition of acceleration, right? This is a general everyday kinematics equation. These two really tell me about how my velocity changes. In fact, I could change out the velocities to delta v's if I really wanted to. So like this one, because I could bring the v initial over. It gets messy with the second one, but so this says, hey, your velocity changes because of time. The rate you're changing and the time. That's that first one. So if they'd asked me how long it took to stop in time, I would have thought of this one.
And the second one changes with distance.
Changes with distance. And the squares are there to make the relationships work out. But really it's the same idea. How does your velocity change at this rate for this amount of time? How does your velocity change at this rate for this distance? Or displacement, really. Okay. And I plug in and get an answer for delta D since it's the only variable in there. And then I do it again for 32. Most common mistakes will be to forget to square things or to forget the negative sign there. Both will come out badly if you do that. Alright. Cooking class. Ice cube, microwave oven. Oven delivers as much power to the ice cube.
Whole mac, baby.
And it takes this many joules to melt it. And how long? Oh, you guys notice what did they put their default units here in? Minutes. What do we use? Seconds. So make sure you convert your answer to minutes. That could mess up a lot of you.
Oh, that could off us.
So, $18. I would put the definition of power here. Rate, work, / energy is done. And then I would go here to my equation sheet and notice I only have one equation under power. And it says all these things about change in work over time, change in energy over time, or force times velocity. Oh, that's the one you need for the fly. So I'm going to use power equals change in energy over change in time. I'm looking for time. I'm going to rearrange. Then I'm going to put in my values. 33,200 joules. 2,200 joules.
What are you?
Over 135 watts. I'm going to get a change in time, but it's going to be in seconds. Then I'm going to convert it to minutes, and I'm going to go home happy.
Yeah.